So welcome back, everybody, for the last lecture of this day. I will talk about zero-sum problems. And so this is the general theme of the lecture series, which I will present together with Professor Tangadurai from HRI. And this first part is somehow an introduction and overview. So what are these questions, zero-sum problems, all about? So the general situation is, so let G plus be a finite abelian group given a collection of elements G1, Q. We want to know, is there a certain subcollection whose terms sum to 0. And so 0, maybe I should add this here, so this is the neutral element of the group. I will be a bit more precise later what I mean with collection. So a finite abelian group, we have some elements of this group, and we want to know, is there a way to write 0 as a sum? One question one could ask right away, are these conditions by finite and abelian groups? I mean, one could do it maybe for any group. Well, if one drops finite, so 2 remarks for G infinite, the questions would need to be modified to be interesting. What do I mean with this? Well, usually if one does not impose some additional restriction, it just won't work, and it's easy to see that it won't work. For example, one could consider a G0 and G finite, so to say G0 and G, and where G is infinite, but G0 is finite, and all the Gi are in G0. So this would be something that would make sense, or at least sometimes. So one could have an infinite group, but only consider subcollections, so to say, of a fixed finite set. And the other thing is, well, most problems could be considered over finite groups, but we won't. So these equations are also interesting for groups in general. Then usually one would not write them additively and would rather say one wants to find a product 1 subcollection. But this will just not be in the scope of the lecture. It's an interesting problem, but we will not consider it. So this is the general setup. So we will always have a finite abelian group. Then we have a bunch of elements. And we ask the question, can we write 0 as a sum of a subcollection? So what's with this word collection? Well, basically, there are two cases. What's the main question here? A main question that arises here is, do we allow repetitions of elements or not? Are these elements G1 up to Gk that we consider pairwise distinct, or do we allow repetitions of elements? So these are the two main decisions to make. So if we do not allow a repetition, we could just consider it as a set. If we do allow repetitions, we will usually use the term sequence. And one point to observe is that since we are mostly interested in questions which concern the sum of the elements, and the group is abelian, usually we do not care about the ordering of the elements. So in the case we would consider for non-commutative groups, there are additional aspects. So one could fix the ordering of the elements or allow flexibility regarding this, in particular when one chooses the subcollection. But in the abelian case, there are basically only two cases. So either we allow repetitions or we do not allow repetitions. So the collections. So there are two cases, repetitions of elements are allowed. So then we talk about sequences, we talk about sequences in this case, and repetitions are not allowed, and we talk about sets. It's mostly somewhat intuitive, but sometimes it's convenient also to have some alternate terminology, and we talk here about so-called square-free sequences for reasons I will explain later. Sequences, and here sometimes the terminology multiset is used. I mean, it does not really matter all that much. I mean, this and this is not strictly the same, because here most people might assume the terms are ordered, but as I said, this is really immaterial, and in our formalization of sequences, the terms actually will not be ordered. So repetitions allowed, and we have sequences, repetitions not allowed. And what is it with the subcollections? As it here, certain subcollections. So yes, so we consider subsequences or subsets, depending on what we choose first, and possibly impose an additional condition on usually on the length or the size cardinality. If it's a sequence, we would say the length, and if it's a set, then it would be the cardinality of the subset. But there are also other ways to impose restrictions. For instance, one might say maybe one considers certain elements of the groups with a larger weight, for instance, groups of low order, one might give a higher weight to them than to groups, to the elements of the group with large order. But I will not go into this as it will not be a major concern, at least not at the start. And so what types of problems? So here I did not really make it precise, but one might guess it. What is it with this collection? So typically we do not care about a specific collection, but we are looking for some Ramsey type results, as in the first lecture of today. So the idea is if the sequence or the set is large enough, then we certainly can find a correct subcollection that we like. And then we ask, so the result that the subcollection exists in this context, typically they are not too difficult to obtain, but then the main problem is to find the exact threshold that guarantees the substructure that we seek. So usually we seek results that are Ramsey-like. In the following sense, then something like one observes if K is large enough, then every collection G1 up to Gk contains this type of subcollection. So one observes this. And now then the goal determine the best possible K, of course, given the G. So maybe I should add this here. Of course, the G needs to be fixed. And for this type, so to say one can insert various things. Well, I already said it at the start. Mostly we will be interested in the problem that the terms sum to 0. Okay, so I'm not sure. Does it really work now? Well, yes, I think so. So is there a certain subcorrection so whose terms sum to 0? So I imposed this already, more or less. But one could also consider other variants. So, but let's really do this for this case. Has a subsequence of whose terms sum to 0. So let G be a finite abelian group. Then for K sufficiently large, the sequence G1 up to Gk certainly contains a subsequence let's write it like this, G1, Gj1 up to Gjl, such that Gj1 plus Gl is equal to 0. I mean, why is this true? It's one could use some kind of pigeonhole argument. The group is finite. So if the sequence is very long, then there is one element that will be repeated often, at least one element that will be repeated often. So for instance, if the sequence has length 5 times the order of the group, then there will be at least one element that is repeated 5 times. Okay, this would, I mean, it would be 4 times the order plus 1 would be sufficient, but I mean, let's say yes, but I mean, just to get the idea across. So then one element is repeated often, and as in any finite group, every element has finite order. So if I take the sum of an element sufficiently often, then it will be 0. And in particular, the order of the group itself has this property. So if, for instance, I take a sequence of length order of the group squared, then I definitely find one element repeated the order of the group times, and the sum of all these will be 0. So in this case, this is, so maybe let's call this a lemma and give a proof, even though it's simple. So say k is equal to squared, then there is a j that appears at least order of the group times and to 0 for each, for every j in J. Thus, choosing the subcollection to be formed by J copies of G achieves this. But of course here I was really very wasteful, possibly very wasteful in my argument. I mean, I was definitely wasteful because I did not even bother to make sure to choose the smallest value here that would guarantee this. So I could take something, I don't know, order of, I mean, I could economize something here. And then also, I mean, there should be interactions between the elements. If I have many different elements, for instance, I can never have an element and its negatives, then I can stop immediately and so on. Once this right away, this won't be the right value. So the question is, what is the best possible k? What is the best possible k for a particular g? And one calls this one calls this Tenpart constant of G denoted So maybe at first one might think, well, for finite abelian groups, that won't be that complicated a problem, and it should be possible to give an answer. But as it turns out, the problem is quite tricky, and there are many groups for which this value is simply unknown. There are also various results known, and we'll see some of them during the lecture, not this lecture, but during the series of the lecture, in particular in the next talk. There will be results on the Tenpart constant. Maybe towards the end of this lecture, I will also say something already in this direction if time permits. But so this constant is investigated since about 50 years, and various things are known, but many problems are still open related to this group. And so here it is for sequences. So if one has this, I phrased it for sequences, and then this gives the so-called Tenpart constant. The question is here is that one has this same thing more or less with sets. Does this question also make sense for sets? Well, for sets, it's even in some sense somewhat easier to argue that it will always work, in the sense that if a subset, if one has a sufficiently large subset of a group, there will definitely be a sub-subset whose terms sum to 0. I mean, it's strictly unavoidable, because if I make the cardinality too large, so as large as the entire group, then I have the 0 element itself, and I just take this one. So in this case, if I take sets, then the existence, so to say, of the constant or of this bound is obvious, but then one can also ask what is the exact value. And this would be another type of problem one can consider, and this goes by the name of Olsen constant. For sets, so this is the so-called Olsen constant. And we will also talk about this constant in the sequel, in the, I think it's planned for the 5th lecture, if I recall correctly. Oh no, excuse me, in the 6th lecture, I think, in the penultimate one. But so this is the general setup, and now maybe let me make some kind of interlude on finite abelian groups, just mostly to fix terminology. I won't do many proofs on finite abelian groups, but I basically just want to recall the structural description for finite abelian groups and introduce some terminology related to this. So finite abelian groups, here this is also a thing which makes finite abelian groups much easier to study than abelian groups. So for finite abelian group, which makes finite abelian groups easier subject to study in this context than finite groups. So for finite abelian groups, there is a simple structural description, which is not the case for groups. So what's the simplest example of a finite abelian group? That would be a cyclic group. And then what if one has this example of cyclic groups, how can one get more finite abelian groups from cyclic groups? Well, one could consider the direct product or the direct sum of several cyclic groups, and the result I will recall says that, well, basically that's all there is to it. Every finite abelian group can be decomposed into cyclic groups, and then there are one or two, so to say, canonical ways to do this, and this gives rise to various parameters of the group. So this is finite abelian. So structure theorem. Which is, so it's a very classical result. I believe it's originally due to Kronecker. So somewhere in the 19th century. Let G plus be a finite abelian group there exist unique integers 1 less than n1 and r such that G is isomorphic to the direct product of cyclic groups of order n1 up to nr. Of course, this also is addition as operation, otherwise it would not even be a group usually, or at least not in a natural way. So one has this result. And with this also this, with this condition, in addition, it's uniquely determined. But this additional condition is also needed, otherwise one would have different ways to decompose a group into a product of cyclic groups. I mean, this is basically using the Chinese remainder theorem, one can see this right away. I have a cyclic group of order n, and if n is composite, I can decompose this into cyclic groups of prime power order. So then I can do this here, and then I can recompose also in different ways. So, but if one imposes this condition, then one has uniqueness. And since this is unique, the parameters that appear here are of some relevance, and they have names. So one calls R the rank of G, and one calls NR the exponent of G, and denoted RG, denoted exponent of G. And this exponent has the property that it is the least common multiple of all the orders of elements of the group due to this divisibility condition. So note, so the exponent of G times G is equal to 0 for all G in G. And xg is smallest positive integer with this property. So this would also be a more intrinsic way to define the exponent. One could define it as the least common multiple of all the orders of the group. And let me make a quick note here. If one looks at this, one could ask, what is about the group with a unique element? Because here, I mean, I impose n1 is strictly greater than 1, so how do I get the group with a unique element? And here, I mean, it would correspond to the empty product. The only issue is that then it's not clear what the exponent should be, but just to be in the safe side, let's say for G, a group with one element, we have how we said, a rank of G is equal to 1 and 0, excuse me, and the exponent of the group is equal to 1. And maybe let's. So then there's no confusion about the case of groups with one element, but I mean. So this is one way to decompose groups. So another would be, also there exist prime powers Q1 up to Qs such that G plus is isomorphic to the product 1 to S set Qi set, and the Qi are uniquely determined up to ordering. And here S, the S here is called the total rank of G, denoted as the G. So there are two different notions of rank. And one can ask the question, when would these two be equal? And the answer would be that they are equal if and only if all the Ni here prime powers and then necessarily powers of the same prime. So in particular, the exponent would be a prime power, and one calls these groups P groups, and they play an important role, in particular in this context. So we can now also maybe briefly reformulate this result, because it will be often useful. So one could also reformulation. So let G be a finite abelian group and there exist E1 up to ER such that in G such that 1 is less than the order of E1 divides order of ER, and G is the direct sum of the cyclic subgroups generated by the EI. And the order, moreover, moreover, the orders of EI are uniquely determined. Right. So what is the order of an element? So odd G is the smallest n greater or equal to 1 such that ng is equal to 0. And such a collection of elements, we say that E1 to ER is a basis of G. Somewhere in analogy with the vector space terminology of, even though this is of course not a vector space. I mean, it would be a set module, but it's not a set module basis because, of course, the Finitebelian group is not a free set module and it does not have a basis in this sense, but one still uses the term basis. More generally, one would like to use a notion of independence of elements. So a family F1 Fs over G is called independent if sum I1 to S AI Fi equal to 0 with AI in Z implies AI Fi equal to 0 for all I. And here it is AI Fi and not AI. So it's merely AI Fi is equal to 0 and not the stronger condition that AI is equal to 0. The later one would be usual linear independence over Z. But it would make little sense to consider this condition for finite abelian groups because then there are no independent elements whatsoever. Because I can always take, if I take for each AI the order of the element, the sum will be 0. So then nothing is ever independent, except with the possible exception of the empty set, but maybe that's not the most interesting thing to have then as a notion. So therefore, our notion of independence has this condition. Yes. So, and generally, and as in the vector space case, an independent generating set is called basis. Remark, the cardinality of a basis is not unique. In general, indeed, R of G, so the rank is the smallest size of a basis, and the total rank is the largest size of a basis. And one has Rg equal to star of G if and only if the exponent of G is prime power. One says G is a P group in this case. And more specifically, a 2 group, a 3 group, a 5 group, depending on what type of power, what the prime is to which power. So if the exponent is a power of 3, then it's a 3 group. And the exponent enters into the definition of various zero-sum constants. And so this was also one reason why I wanted specifically to recall the definitions of this notion, in particular of the exponent of the group. So now with this I end the interlude on Finitebelian groups, and now we give somehow several definitions of zero-sum constants. So let's say the general setup for setup is not the best word. It's a general definition of a zero-sum. A general definition of zero-sum constant. This is certainly not the utmost general definition, but most of the constants we will consider, at least those for sets, fall under this definition. So let is always J be a finite abelian group. Let I be a subset of the integers. So usually of the non-zero integers, positive, sorry, the natural numbers, I wanted to say the non-zero natural numbers. And now the question is, let Si G and union infinite plus infinity be the smallest element such that each sequence G1, Gk of size at least of size k at least Sij has a subsequence with some 0 and length in I. So what's with the plus infinity here? I always consider only I always only consider finite sequences. So the plus infinity here is just introduced as a fallback to have always a valid definition. So the point is, it is possible, as discussed implicitly a bit earlier, but and we'll discuss it in detail right afterwards. So if I choose this I in a way that is not good, so to say, related to the group, for instance, say let's say I take a group which has two elements, so the neutral element and one of other two, and then I take a sequence which only contains the non-zero element and I repeat it. Then all the zero-sum subsequences I can find, they will be of even length, because the only way I can have zero is I take this element twice. So I can never arrive at something that is zero with an odd number of elements. So and then if I take for I the set of all odd elements, so just 3 or 19 or whatever, then I will never find, so to say, a sequence which has this property. And so I say then it's plus infinity, because then this entire thing becomes vacuously true, because there is no sequence which has these lengths, and then the conclusion is vacuously true. So this is just, so to say, to have a fallback in case the constant, so to say, does not make sense. But as we will see right away, there is an explicit way to characterize for which these constants are finite, and then this problem goes away. So maybe I will say this right away. One can show lemma SIG is finite if and only if I contains a multiple of xg. Maybe if time permits, I will give a proof, but I will say something else beforehand. So, now one has this definition for whatever set I, but maybe some sets I are more natural than others to consider. So there's no particular good reason maybe to study these constants for 3, 7, and 29 or something like this. Say so some important special cases, some important special cases. So one has, so if one allows all the integers, so non-zero integers, this is the EG. So this is the Tenpart constant. So here you see I take for I the set of all the positive integers. So I have no restriction on the length at all. So it merely means there is a subsequence whose sum 0, because I do not restrict it in any way. So what else? Our argument, when we argued that the Tenpart constant is always well defined, so there we constructed, in fact, or we argued that we always can find a zero-sum subsequence of length equal to the exponent of the group. So also this makes sense. S exponent G. So and this is sometimes just called S of G, and this is sometimes called the Erdős-Ginzburg Sieve constant. The Erdős-Ginzburg Sieve constant. And actually, to be very precise, the way I really gave the proof, I did not use the exponent, but I used at that point the order of the group because I had not yet introduced the exponent. So also this constant with the length, the order of the group makes sense, and this is sometimes called ZS of G, so the zero-sum constant. So this is some zero-sum constant. So this is also a very classical object. So it is called just zero-sum constant because it was really one of the first that was considered. And these days, it's known that these two are very closely linked. So they are often studied together, but this is a non-trivial result due to Go that one can link these two. And then there's also, if one allows, for instance, the set 1 up to exponent of the group, so this is sometimes called eta of G. It's denoted eta of G, and it doesn't have a particular name, so it's just a eta invariant. So maybe if somebody has a good idea for a name, it might get one at some point. But by contrast, the sequences here have a name, so one calls these sequences short, so short zero-sum sequences. So a zero-sum sequence of length at most exponent of the group is called short. These are the important special cases of constants that received attention in the literature, but there are various other examples too that are interesting. Other examples. For instance, if one takes S exponent of the group n, so one just wants some multiple of the exponent of the group, not necessarily the exponent. So this is sometimes called S0 of G. It does not denote the S0 of G. It does not have a particular name to the best of my knowledge. One can also study as dn of G, mostly for GCD D and exponent of the group not 1. Well, maybe that's not necessary. Let's just for some D. This is also, this is always well defined because it's always finite. Well, because I can always manage that this is a multiple of the exponent. And by contrast, there is still another one, which is defined in the dual way, in the other way around, the G, like this. So one wants to avoid the multiple of something fixed. Then this one for D does not divide the exponent of the group. One can also do it if D divides the exponent of the group, but then one will find that it's infinite, and this is maybe not. And this is sometimes called ED of G, and there are still various other constants. For example, one has the exponent, one has some multiple of the exponent. One could also ask what specifically do I have a subsequence of lengths. For instance, one can have S2 exponent of the group G, or SK exponent of the group, and so on. Also here one could impose, one could take other intervals here, or one could consider S1 up to some L, G, where L is greater or equal than the exponent of the group. In principle, one could also see that for something that is strictly smaller than the exponent of the group, but then right away with this lemma, one sees that it's infinite. So, therefore one does not really start it. So I think I'm coming close to the end of the time. So I gave here a first overview and introduced some notation for Finitebelian groups. And you find here the definitions of the constants. So, and as I recalled, basically here I talked about the problem for sequences now, but all these questions also make sense for sets. So what will be the plan for the following lectures? The next lecture will be mostly concerned with the Tenpart constant. We will then, and maybe we'll start something on this, then we will go to classical results on this constant and classical results on this constant. Then there will be one lecture which discusses more recent developments related to these constants. Then we will turn our attention to problems with weights. I did not yet say what are weighted zero-sum problems, but these are problems. This was a variant of zero-sum problems introduced by Professor Adhikari, where one allows not only that the sum is taken, but for instance, one also allows differences. For instance, one does not insist that the sum of all the elements is 0, but maybe I can choose the element or its inverse and I want to have 0, then one talks about the plus-minus weighted zero-sum problem. Then one can also consider more general problems related, more general sets of weights. So this will be, also a lecture will be dedicated to this. And then there will be a lecture which gives results on these constants, on the analogs of these constants in the set context. So not sequences, but sets. And then there will be a final session which discusses some applications of these problems, and maybe also will serve somehow as a wrap-up session, or also to give some information on questions that might have arisen during this week. So I will stop here with my introduction. Thank you for the attention.